Welcome. Let's take a look at number 2. A manufacturer claims that the lifespans of a certain appliance are normally distributed with mean 48.2 months and standard deviation 7.1 months. So our random variable X is going to represent the lifespan of one of these appliances. So let's start by writing down our population parameters. So mu, the population mean, is 48.2 months. And sigma, population standard deviation, is given as 7.1 months. The distribution is normal. So our axis here, X, is our random variable, the lifespan of an appliance. The center of the distribution is the mean. So in this case, 48.2 months. And the sigma describes the spread of the graph, but we are not going to put any additional information on the picture just to make it a little bit cleaner as we look for the value that they're looking for next. So B, find the lifespan that cuts off the top 5% of lifespans from the rest. So the top 5% of lifespans would be somewhere over here to the right. And we don't know exactly where the value is that creates an area of 5%. So we don't have to have perfectly drawn to scale pictures. The idea is that I know that this value for the lifespan needs to be somewhere to the right of center because this top area, so when it says top, it means to the right of the unknown value. So I need that area to the right of the unknown value to be 5%. All right, so when we're looking for unknown values, data values, we always use inverse norm. But inverse norm is going to require us to tell our calculators the area left of the unknown value. So if 5% of appliances last longer than that value, then 100% minus 5% would be the other 95% of appliances that would have lifespans less than that value. So as percentages, 5%, 95% together would be 100% of appliances. So every unknown value X separates a graph into two parts, the part above it, 5%, and the part below it. So I'm going to repeat all that here, but in decimal form. So if it says top 5%, it means that the area to the right of the X value we're looking for needs to be 5%, or in decimal 0.05. So top. All right, but to work with inverse norm, we want to know the area left of X. So the rule of complements in decimal form is 1 minus. So if we take 1 minus the area to the right of it, we'll get the area to the left of it in decimal form, and that will be 0.95. So that's our 95% in decimal, 0.95. All right, so now we can find X. So we can inverse norm, always inverse norm the area left of what you're looking for, and then we'll need to put in our mu and our sigma. So we'll inverse norm, not that number, but 0.95 for the area left. And the mu is 48.2, and then our sigma of 7. All right, so let's try that. So we'll inverse norm 0.95, comma 48.2, comma 7.1. And because my calculator is so small, I think my decimal point there is not a comma. So 48.2, oh, I think I'm good, comma 7.1. All right. And it says to round to 1 decimal place. So that's going to be 59.9. And we'll include the units here when we write the sentence, but that answer is looking like 59.9. Okay, actually I'll write the units here as well. So 59.9 months is the lifespan that cuts off the top 5% of these appliances from the rest. So that lifespan of 59.9 months represents, so what would its percentile value be? So remember, percentile values, they represent the percentage of data below that value or to their left. So if 95% of the data is to the left of that value, that is the 95th percentile. Okay, and we'll try another one. So number 3, the mean weight for newborn elephant calves is 225 pounds with a standard deviation of 45 pounds. So let's start with writing our population parameters. So mean is 225 with a standard deviation sigma, population standard deviation 45. And I'll label here on our first graph, so our x-axis is the weight of a newborn elephant calf. The center of the distribution would be the mean of 225. And again, we won't worry about writing any other values on the x-axis here. We'll just focus on the values we need for the problem. So find the probability randomly selected newborn calf weighs less than 175 pounds. So again, I'm not trying to draw these to scale. If that's 225, 175 is somewhere to the left of it. So we can just put it anywhere here just to get a visual of what we're looking for. So if we're looking for the probability that a calf weighs less than 175 pounds, those would be calves with weights to the left of the 175. So in theory, theoretically, the graph does continue indefinitely there to the left, so negative infinity. So that's going to be our lower bound and then our upper bound. So if we're looking for probability, it's the normal CDF function, where we give our lower bound, so in this case, the negative E99, the upper bound, the value 175. And we also need to tell the calculator the mean of the distribution and the standard deviation. Okay. So let's go ahead and get that one typed in. So normal CDF for probabilities, negative E99, 175, 225. All right, in decimal, that is 0.1333. So as a percent here, 13.33% of newborn calves weigh less than 175. All right, C. Find the weight that separates the bottom 85% of weights from the rest. And we will round this to the nearest whole number. All right, so let's put in our sort of x-axis here. 225 is the mean. Now, if we're trying to separate the bottom percentage, so bottom percentage would mean that the area to the left, so below the unknown value, needs to be 85%, in decimal 0.85. So now we can go straight to inverse norm to find a data value, because we need to enter area to the left, and we have that value, 0.85. And then, of course, the mean of the distribution and the standard deviation. All right, so inverse norm, 0.85, 225, 45. And we said round to a whole number, so we'll go 272 pounds. I'll be interpreting that in a moment. So let's see if this answer makes sense. So if that's 225, 272 would be to the right of that. And the bottom, so the area to the left of that is 85%. Okay, so my picture is a little bit squished here, but all that area to the left is 85%. So this unshaded area to the right, those calves that weigh more than 272 pounds, that's 85%. 100% minus 85% would be the remaining 15% of calves. So that value of 272, the percent of data to the left of it, 85%, means that this is the 85th percentile value. So that's this interpretation part. So what could I tell you about the 85th percentile weight? So approximately 85% of newborn calves weigh less than 272 pounds, which means that approximately 15% weigh more than 272 pounds. So again, every data value separates the graph into two parts, the part to its left and the part to its right. Okay, one more, number 4. All right, so heights of adult men in a population are normally distributed with mean 70 inches and standard deviation 4 inches. An architect wants to make a certain door designed to allow 95% of men in this population to pass through the door without needing to bend. Find the required door height. All right, so let me just start with this population of men. The mean height, 70 inches. Standard deviation, 4 inches. So if X is the height of a man in the population, 70 inches in the center of the distribution is the mean. All right. So they want to make a door so that 95% of men can get through the door without bending. All right, so the door needs to be tall enough so that 95% of men can get through. So if the door was 70 inches, that wouldn't be good because half of men are taller than that. So I'd have half of men needing to bend to get through a 70-inch door. So I need the door to be taller. So somewhere over here, I'm going to have a door height that allows 95% of men, so this would be the area to the left of that unknown value, the door, that area to the left would have to be 95% of men. So another way to say this is 95% need to get through the door without bending, which would mean that those taller than the door, that would only be 5% of the population. So 5% of the population will be taller than the door. So they'll have to bend to get through the door, but 95% of the men can walk through without bending. Okay, so if we want to find a data value X, the inverse norm, the area to the left of the unknown value, we want that to be 95% or 0.95. And then we need to put in mu and sigma. And we'll round to a whole number here. So inverse norm, 0.95, comma, 70, comma, 4. So as a whole number, it looks like the door is going to need to be 77 inches. All right, and then you have some examples of using normal CDF and inverse norm on normally distributed variables.